Okay, let's just dive right into this explainer and completely demystify how large language models actually work beneath the surface. It's so easy to look at the systems we use today and assume there's some sort of omniscient intelligence living inside our computers. But to truly harness the power of these models in a professional or enterprise setting, we need to completely shatter that illusion. Today, we're going to tear down the engine, look at the actual mechanics of generation, and learn how to steer these systems effectively.
So, we've got a super clear roadmap for today. We're going to cover 1. The evolution of AI, 2. The next word engine, 3. Pre-training versus post-training, 4. The non-deterministic problem, 5. Engineering the prompt, and finally, 6. Advanced prompting techniques.
Section 1. The evolution of AI. We're mapping the leap from manual features to generative models.
Let's start with how we actually got here, because the leap across these technological epochs is just staggering. Look at pre-2012. Everything was manual. If you wanted a machine to recognize a cat, you literally had to code its features by hand. 4 legs, 2 eyes, fur, the whole shebang. Then around 2012, boom, we hit a turning point with computer vision and models like ResNet introducing transfer learning. You could actually fine-tune a pre-trained model. But natural language processing, still incredibly hard and expensive. It wasn't until 2018, with the famous Attention is All You Need paper and the birth of transformer architectures, that things really shifted. That breakthrough let models ingest massive amounts of internet text, which drops us right into the 2023 era of generative AI and real-time voice agents we're living in right now. To put that timeline into perspective for where we are literally today, let's look at enterprise voice AI applications. If you're building a voice agent, your system has to respond to a human in under 600 milliseconds for it to feel natural. 600 milliseconds, that is a massive technical constraint, and it's exactly why developers today are constantly favoring much faster models, like Gemini Flash, over standard, beefy models that might take a full 2 seconds to reply. Speed has become just as critical as accuracy.
Section 2. The next word engine. Let's shatter the illusion of machine reasoning.
Now here is the concept that is absolutely going to shatter the biggest illusion about AI. It doesn't actually think. No, seriously. At its core, a large language model is literally just a next word prediction engine. It takes your text, scans its massive mathematical map of internet data, and just calculates the highest probability for what the very next word should be. So if you type Narendra and the word Modi has followed that millions of times in its training data, it spits out Modi. There's no actual reasoning happening there. It is just highly sophisticated statistical prediction.
And because it relies completely on next word probability, it has some pretty massive blind spots. For instance, the model really struggles with a language like Sanskrit. Why? Because placing a new word in Sanskrit can completely shift the contextual meaning of the whole sentence, which is basically a nightmare if you're predicting things sequentially. It also struggles with Thai, since Thai lacks traditional spacing between words, and get this, a raw language model can't even inherently do basic math. If its internet training data had some weird repeating pattern where 1 + 1 = was followed by 11, the raw model would confidently tell you that 1 + 1 = 11. It's just predicting text patterns, not computing integers.
Because of these blind spots, AI expert Andrej Karpathy suggests a really brilliant mental framework. He says, always treat the model as an intern. Think about it. You would never hand a critical, highly complex task to a brand new intern and just expect flawless, unguided brilliance without checking their work, right? You've got to guide them, structure the task, and verify. Section 3. Pre-training versus post-training. Building the engine versus building the assistant. So if it's just this raw prediction engine, how does it become the super helpful assistant we use every single day? Well, it's a 2-step process. First up is pre-training. This is massively expensive. We're talking sometimes upward of $80 million. This is the phase where the model basically reads the entire internet and turns into that raw prediction engine. But that is not what you interact with. You interact with the result of post-training. This is a much cheaper, highly targeted phase using supervised fine-tuning. This is where engineers integrate actual tools. So if the model sees a math problem, it knows to go ping a calculator instead of just guessing the next word. Post-training is also where they bake in safety guardrails, so the model politely declines if you ask it how to say hotwire a car.
Section 4. The non-deterministic problem. The chaos of unpredictable outputs.
This foundational architecture leads us right into the biggest conflict when using generative AI in any professional pipeline. So you go into an AI chat right now and type, "Who is Narendra Modi?"
you'll get a great answer. But if you clear the chat and ask that exact same question again, you are not getting the same text. Ask it a third time and you'll get a completely unique third variation. One might be a standard web bio, another an internally generated summary, and the third a uniquely phrased historical overview.
And this non-determinism right here, it's a massive headache for developers. You simply cannot guarantee determinism in an inherently non-deterministic system. Imagine trying to feed AI output directly into a strict formatted database, and the AI randomly decides to add conversational wrapper text like, "Here is the answer you requested," before actually giving the data. Your entire software pipeline just breaks. You absolutely can't plug a raw AI into a production app and expect enterprise-grade reliability.
Section 5, Engineering the Prompt, the steering wheel for a chaotic engine.
So let's talk about the solution. This is exactly why prompt engineering is an absolute must-have discipline. It's basically the steering wheel for this chaotic engine. There are two foundational techniques you need to know. First is zero-shot prompting. This is what most of us do casually, just asking a question blindly with no prior examples. It works fine for simple queries, but few-shot prompting? That's where you actually take control. By giving the model a few specific examples right in your prompt, you're setting the exact tone, structure, and format you expect back.
Anthropic's guidelines actually tell us that providing 3 to 5 clear examples is the absolute sweet spot. Let's say you want the model to do sentiment analysis without it writing a whole paragraph of useless text. You show it the pattern. Input, the movie was bad. Output, negative. You give it a few of those. Then, you give it the actual task. Input, the movie was terrific. By feeding our intern these structured examples, you essentially lock the model into a deterministic pattern, guaranteeing it responds with exactly one word, positive.
Section 6. Advanced Prompting Techniques. Forcing the model to show its work.
Okay, but what happens when the task requires complex, multi-layered logic instead of just simple pattern matching? In the past, if you gave it a logic puzzle, the model would try to guess the answer in one single go and usually hallucinate the wrong result. But researchers found this totally fascinating hack. By just appending the phrase, "think step by step before answering," to your prompt, you trigger what's known as a chain of thought. You're physically forcing the model's next word prediction to output its intermediate logical steps before it spits out the final answer.
This is a real game changer. For example, if you give a multi-step math or coding problem to newer reasoning models, like DeepSeek or OpenAI's latest versions, they will literally output their thought process. It breaks it down. Okay, first I need to double the number 3, which is 6. Next, I need to subtract 4, which leaves 2. By generating the text of those steps, the model gives itself the context it needs to arrive at the correct final output. It turns a complex word problem into a sequence of verifiable, highly accurate steps.
And honestly, the engineering doesn't stop there. Developers are using some highly advanced architectures to tame the chaos. There's self-consistency, which forces the model to generate 5 different answers behind the scenes and mathematically vote on the most common one. Perfect for high-risk scenarios. Then there's prompt chaining, where you have the AI generate an output, pass it to another prompt to critique it, and then regenerate it based on the feedback. And finally, we have RAG, Retrieval Augmented Generation. Since a model's knowledge cuts off at its training date, RAG takes a secure, say 10-page external company document, chunks it up, and automatically injects the relevant text straight into the prompt so the model can read it in real time before answering.
So, as we wrap up this explainer, I want to leave you with a bit of a reality check. You could spend weeks crafting the absolute perfect prompt. You use few-shot examples, RAG, chain of thought, and it runs perfectly in testing. But since these foundational models are continuously post-trained and silently updated behind the scenes by their creators, an underlying algorithm change can literally happen overnight. So the provocative question you have to ask yourself as you build in this space is this: how will you continuously monitor, test, and future-proof your perfectly engineered prompt when the underlying engine itself might completely change tomorrow?